Hello. This will be a fairly long lesson and it lends itself well to video delivery rather than me standing in front of you in the classroom. So the problem that I want to go through is problem 2.6 in your book. It has a lot of subtleties that will take a little while for you to sink in for sure. And those subtleties focus here on the second part of this list. So open up that list. I think that's the hardest part right down here. And it's not hard, it's just conceptually hard. Mathematically, it's not hard at all. This stuff is a little harder mathematically, but it's kind of robotic for us here. So we'll try to walk through everything here. Finding the principal stresses, ordering them on a number line, doing that through that function, and then using it with the cofactors. And then we're going to find the net Sigmaxpxp on that plane. And this one, it's kind of a nice problem here because he gives us the full N matrix, which is the T matrix for us. The transforming matrix, right? All right, so let's set it up, and I'll show you how to do this in GeoGebra. You don't have to use at all GeoGebra for this part, but I do think you should program this. So I programmed it twice, just because that's the kind of guy I am. So I did this in MathCAD, and then I did this in GeoGebra, but you could certainly use MATLAB or any other language that you want. The first thing that you want to do is put in the stress matrix here. It all starts with that. To put in a matrix in GeoGebra, we just use the curly bracket. So trial matrix is curly brackets for the whole thing, and spaces are ignored. And then curly brackets per row. So if I wanted to do 25, 10, and 15, for instance, that would all be in one row. And then a comma, and then another set of curly brackets. 10, 0, 0, and then another set of curly brackets. 15, 0, and minus 20. All right, so that seemed to work pretty well. I'll just get rid of that. We need the principal stresses and these invariants. So how do we get the principal stresses? Well, there's two ways of doing it. So the first way of doing it is this function here. So this function is plotting sigmas. That's my x value on Mohr circle. So it'd be sigma cubed minus invariant 1 sigma squared plus invariant 2 sigma minus invariant 3. But obviously I need the invariants. So let's take a look at those invariants here. So the invariant 1 is simply sigma xx plus sigma yy plus sigma zz. Now, I showed you how to type in that matrix, but what I didn't do that for this stress matrix. You'll see what I did here. You could do it either way. For my stress matrix here, I actually said, I used the curly brackets, of course, but I said it's sigma xx, sigma xy, and if you're wondering how to get the Greek letters, they're right here, or on the very, very right edge of any input bar. And that's kind of handy because I need these numbers. So either type in these numbers here as scalars and then pop them into the matrix, or type them in as the matrix like I did for that trial and then pull them out as scalars. Okay, either way is fine. Whatever is easier. I actually think this is just slightly easier putting it in here, but it's up to you. All right, and then we got the invariants here, so you could test that. Your invariant 1 is 5, invariant 2 is minus 825. That's just this kind of repeating pattern, which is quite beautiful. XY, XZ, YZ. See how that works? There's always these cyclic patterns, IJK. Invariant 3 is the determinant of the stress matrix. So here's another beautiful thing. In MATLAB or in MathCAD or in GeoGebra, we could just say determinant. And we actually don't have to punch out the determinants as we do for these little cofactor matrix. So get that invariant 3. And then there's our plot of the stresses, and I mentioned this last time, it's a hugely varying oscillating curve, but where it zeroes out, that is the answer. Now you could do this and zoom in and kind of approximately get that, right? But I just threw this plot up there just as a picture. I didn't actually use this plot. I know exactly where these things are going to cross because of the second method. So the second method uses the Q value, the R value, and this is the cool one with the 227s. How often do you see 227s in an engineering formula, right? There's the Q value, the R value, the S value, all of that. And then the A1 value, which is the determinant of these A1 matrices. And these are these cofactor matrices. So I programmed this. Don't type this in. That would be terrible. So absolutely do not do that. Let me give that a little bit of thought what I did there here. X of sig 1. So okay, now I remember. All right, so this method here, which is under our last handout here. I think it was here. Maybe it was on 5. Sorry, should have opened that one up. These, here we go. So these angles, these sigmas, they come out as A, B, and C. And they might be in any possible order. A doesn't necessarily have to be the first, and B or C. It's like I mentioned before, a robot spitting out eigenvalues. So, and also here, I always do this. Don't forget the minus sign. It's positive, negative, positive, if you sort of remember that from the cofactor rule way back when. So the moral of this story is that I did not use these functions. I used the answers, but I looked at these stresses first. So these stresses here are, there's the first one, sigma A, sigma B, there's the 120, and there's the 240. So I looked at these, just visually looked at this. I did not do this robotically, and I said, okay, on the number line, what's going to be sigma 1? And that's the most to the right. Whether it's positive or negative doesn't matter, but it has to be on the right side, like 3 o'clock over here. So it's clearly sigma A. The third one at 9 o'clock, the most left one, is clearly sigma B. You see that? And sigma C. Now, I don't even want to begin to try to program that. So what I did was I dropped down this point here, which is sigma 3. You could see this point here, which is sigma 2, and this point, which is sigma 1. And I just manually said, all right, sigma 1, you will be sigma A. Sigma 3, you will be sigma B, right? Because you were the worst. And then sigma 2 is the middle one. All right, so those are the stresses, and that function corroborates my cofactor thing. So these are two independent checks on the principal stresses, and I do want you to do that. I want you to get the principal stresses two different ways. So, it just screams that you gotta, I guess you could program that function on a calculator, but I really want you to program this. You don't have to draw all the pictures for me, but I want you to program it. Okay, so the next thing is looking at that problem statement. What was the problem here? So determine the stress matrix in the x prime, y prime, z prime system. We already did step B. We got the invariance. So let's do the new stress matrix. Well, there's two ways, of course, of doing that. Well, actually, there's a third way, but I haven't quite figured that one out yet. The two ways of doing that are the easy breezy way, which is stress nu here. So stress nu is simply the T matrix times stress times the T transpose matrix. And I just called that T transpose here as transpose of T matrix. So I'm really using GeoGebra just as a programming language here and a little bit on the plots here. But like I said, if you don't want to use GeoGebra, you can go to MATLAB. But this has some huge advantages in terms of the graphics and the ease of which you could look at these angles. So the stress matrix is done here. We should also notice that this one here, the stress nu, that is sigma x prime x prime. That's 4.14. So that is the unambiguous one perpendicular to the plane on the oblique cut. So we've talked about that a lot. You could program this also, and here are the clunky transformation equations. So you could use, and I want you to do this, I want you to program the clunky transformation equations, and I get 4.136, and you could see it right here, 4.136. I also programmed that here in GeoGebra. So there it is, 4.146. And that's the exact same equation as you could see here. Just a little bit on, I forgot to mention something kind of important. When you're doing points in GeoGebra, they should all start with a capital letter. Sorry, I should have told you that. Don't use a Greek letter here. Just use a capital letter. So that's one of the only kind of like quirky things that, well, I guess there's other ones, but that's a quirky thing that drove me crazy. I couldn't figure it out. So I use sigma S instead of the Greek letter sigma. And once again, the Greek letters are down here, like in the input. You can see them all in here. All right, so I programmed sigma prime x prime, and I programmed tau net. Now, tau net is special. It's not two mutually perpendicular taus. It's the square root of the sum of the square roots. The square root of the sum of the squares, of the various taus, and that's 6.05. So you're not going to find a 6.05 in the stress matrix here. It's that single value. Now this is subtle, I think, but maybe if you're kind of super comfortable with direction cosines and the like, it might not be so subtle. There's a nice way of getting the direction cosines for the tau net. This has nothing to do with nx prime, and, well, not nothing. It's mutually perpendicular to that. So let me show you in 3D where I'm headed here. View, graphics, 3D. So there is my sigma x prime vector and my tau net vector, and they are mutually perpendicular. But I can, and the sigma x prime uses nx prime x, nx prime y, and nx prime z. This uses t's, the direction cosine, the t's. All right, so how do we get those? Nice handy dandy equation here, which only uses the tau net and the sigma x prime. So it doesn't need the full transposition matrix. It doesn't need the full stress matrix. It's super sweet. So that's why this section is so fun. There's so many nice simplifying methods in this section, which is why I'm spending a huge amount of time on it. So I can get the three T's here. I did it in MathCAD, and I think I did the same thing here. T, x direction cosine. Yep, there it is. Just program that, and you should get the exact same answers, 0.17, 0.42, and you could change, obviously, the number of decimal places. So I would at least like a sketch. If you can't come up with this super cool three-dimensional picture here, and you can hide the circles. You don't need the circles here, but I'm superimposing my more with that. Just at least sketch it out. I think that's very, very important to see this in 3D. All right, now we get into the weeds here. I actually can calculate those actual angles if you want. And this last part, which I talked about in a few spots. I talked about it here in the summary right there. So let's just make sure we did all this. The principal stresses, yes, ordering, sigmas, both ways. Sigma nu, there's the NXPs to the normal, there's tau net, and here I just got the T's. Okay, how did I show this in 3D? I actually didn't, I missed that step a little bit, and here's another small subtlety. It's as simple as this. Sigma x prime x, the x component of that is simply sigma x prime times the direction cosine to the x. And the y part is just that easy. So when I plotted this in GeoGebra here, that sigma point, and remember you got to use a capital letter here. Notice what I did here, sigma x prime point. I just said, give me, it's this, sigma x prime times the direction cosine to the x, sigma x prime, and that's the x, y, and z value. And those are the components right there. So that's kind of super compact, I think. I think maybe that's not head exploding to you, but I think that's really incredibly fast and easy and beautiful. All right, let's go back to our summary. So that's that really fast thing, and show that in 3D. So I want you to show this in 3D. If you can't plot it in MATLAB or in GeoGebra, well, you could certainly do it in GeoGebra. It's super simple. Or Grasshopper or whatever you want to use. The tau is the same way, but don't make a sophomore mistake here. Don't use n's. You got to use t's, because remember the t's are the direction cosines to the blue thing here. So they're different. And now we do this fun check here, and I explained this a couple times, and I do want you to do this check. So let's just talk about this first here. I took that single, well, I did it red last time I taught this class. It's blue in this one here. I took the single blue vector, and I decomposed it into ijk. That is as simple as this. It's just this. Tx direction cosine, Ty direction cosine, Tz direction cosine. That's it. 1.02, 257, and 538. Those are the x, y, and z components of that thing. Or you could do it this way. You could just say tau net, which is a scalar. Tau net, which is a scalar of 6.05. And multiply it by that vector. You just have to set up that vector. And then you get the ijk's. All right, so now what you take that blue thing right here that we just talked about, that blue thing here, and decompose that into 3 pieces. It's got to be 3 because the T matrix is a 3 by 3. And sometimes students wondering, well, where the heck is the 0 from? Well, what I'm doing is I'm decomposing tau net, which is on a perpendicular plane to the sigma prime. No, sorry, it's perpendicular to sigma prime, but it's on that plane, that oblique plane. Tau net lies on that oblique plane. There is nothing out of that oblique plane. There's an infinite number of things in that oblique plane. The SRSS of tau net is in that oblique plane, but there's nothing perpendicular to it. So that's why there's a 0 there. So take sigma nu 1, 2 and sigma nu 1, 3. Sigma nu, this is the 1, 2 and the 1, 3 in the new coordinate system. And let's see where that is. So tau net decomposed here. That's what it is. So it's tau net decomposed. And I like that name. Tau net, the blue one, decomposed into an x part and a y part. So what did I do here? It's just that 0, stress 1, 2, and stress 1, 3, the new stresses. And then pre-multiply it by t transpose, because now we're going from local to global. We talked about this in class. When you do an operation like that, so it's tau x, y, z check is TT matrix times tau net decomposed. That's right here. TT matrix times tau net decomposed. And what do I get? 0, 4, 8, 8, and 3, 5, 8. And what does that mean? These should agree. So the tau xyz vector from tau net should agree to this. 257 and 538. There's the 257 and there's the 538. There's the 257 and the 538. And there's obviously the 1.02, but I've been focusing on the last one. So there it is. That's the decomposed tau net back into 3D, so it has an x, y, and a z component. So that's super cool. I know there's a lot of information. So take a look at that slowly. And I'll just show you one more time over here. Maybe blow this up a little bit. How this all worked in that different environment. One more time, really quick here. So the original stress matrix, you could pluck out the sigmas from here, or you could type in the sigmas and pop it into the stress matrix. The n was given to us here, so that's kind of sweet. Tau net is that simplified method, and sigma x prime, I think you got that one down already. Get the t's, those are the direction cosines to the tau net. You don't need these angles, you really never need the angles. Not even when you're plotting it, you don't need the angles. There is the tau xyz vector. And here's my tau check. And in the book, you'll notice that he did a really minimal check. He said tau net is sigma nu 1, 2. I guess I could have, it's not super minimal. This is 1, 2 right here. This squared, 4.877 plus 3.58 squared should give you 6.05. I didn't program that, but that I hope is intuitive. But if it's not, this one though I'm sure is not intuitive, and that's kind of amazingly beautiful. All right, so I will assign some homeworks and let you attack this in a digital environment of your choice. If it's not 3D plotted on the computer, at least try to get a sketch of the 3D situation. Before we go, I just want to talk about the third axis really quick. I don't know if you'd ever really need it, but what if you wanted the third axis that's mutually perpendicular to the, turn off that plane, that's mutually perpendicular to these two. There's nothing on it right now, so, but let's just say for yucks we wanted to get it. It's not hard at all here. What I did was I just said the direction cosines of the sigma x prime vector is this. It's just the list of the direction cosines. And then the tau net vector is just the list of the direction cosines with the t's. You see that? And the third vector is the first one cross the second. So you have to do a cross product right here. So that's just a cross product, and the command is cross. You know, you could say third check is cross of first vector, which was Sigmaxpxp vector, comma, and then the tau net vector. And then I just took those as the points. Now here's just one tiny little thing that kind of drives me crazy too. If I pull this number out, you need a double subscript. I don't really know why, but here is my third point. So I pulled out row 1, column 1 of this, row 2, column 1, row 3, column 1. I think you have to do that. I sort of vaguely recall that. Third point, here it is. Third vector 1, 1, third vector 2, 1. I kind of want to just use a single subscript here, but I guess they don't want you to. All right, now I'm done. Have fun with it. Enjoy.